Hello everyone. Today I shall take up the topic electrostatic potential energy. And before I go into the details of electrostatic potential energy, just try to recall the gravitational potential energy concept as well as the expression. Now what happens if we drop an object from a certain height? Let me consider an object at a certain height and I drop it. So it moves downward. And how do we define the potential energies? Here the potential energy is mgh and here we take it 0. For smaller distances from the surface of the earth, we take the potential energy 0 on Earth's surface and at a certain height we take it mgh, where g can be taken constant. So distances involved are small. Okay, so if I leave an object, it always moves from position 1 to position 2, and where is the potential energy lesser? In this position. So if it means if I drop an object, it moves from high to low potential energy. Okay, take another example. Suppose I have a spring. It is compressed and I leave it. If it is compressed, we again, if you can recall, half kx square. This is the potential of energy of a spring with force constant k, and if it has been compressed by a distance x. Okay. Now if I leave it, what will happen? It will come to its unextended position where the potential energy again we have taken 0. Now come to this particular chapter. If I have a q charge and I put a charge q here, say at position A, and let me take this q bigger, and this q is very small in comparison to it. Basically what I want, when there is a repulsion, I presume that it remains almost there and this one moves a lot. Okay, what will happen now? Because of the repulsive force on this charge will move. How will it move? It will move away. So maybe it moves along this line. Now again, going by the same logic, if I drop an object, it moves from high potential to low potential. Here it again moves from high potential to low potential. It is also moving from A to B. So at which position can I say that the potential energy of this system of two charges is more? When they are here or they are here? Naturally, all systems try to take a position with lesser potential energy. So it means potential energy is more here, potential energy decreases, and at the cost of it, the kinetic energy is increasing. Speed increases because of the repulsive force. This cube moves from A to B, kinetic energy is increasing and potential energy is decreasing. So naturally, if we leave a system and it is free to move, it will always try to acquire a position with lesser potential energy. So potential energy more here, potential energy less here. If it is minus charge, then now this charge A will come here. It will come closer. Suppose it moves from A to B. So again now potential energy, it always moves towards lesser potential energy. So potential energy will be less when it is at B. Here the potential energy is less when it is at B. So it is moving away, here it is moving closer. So this is how can we define the electrostatic potential energy. I have to take an object of mass m up to a height h. Let me find out how much work will I have to do. Work done is force into distance. mg force is acting on this object in downward direction, the weight. by earth. I have to apply equal force in upward direction and I am displacing it upward. So if I calculate what is the force by gravity, it is mg into h. Final potential energy minus initial potential energy, that will be the difference in the potential energy, which is equal to the work done. Now I am taking it from here to here. Work will have to be done against this force. How much force do I need to apply? How much force do I need to apply here? Force is mg is downward. I have to apply equal force in upward direction. And then h is upward. Where is the potential energy more? At 2 or 1? U2 minus U1 is actually equal to the work done by external force. I am applying force mg in upward direction. I am moving upward. This gives me mgh. Okay, I am applying force in upward direction. Displacement is also in upward direction. The angle between them is 0. So the work done is mgh. And the potential energy will change by the same amount. So in moving this from here to here, the potential energy increases by mgh. Now, let me calculate the work done for this particular configuration. Let it be Q1, and I am taking that Q1 is much larger than Q2 and that only Q2 is moving. Q1 remains there only. Okay, it may move say from A to B. I am taking how much work is done when it is moving from A to B. How much is the force onto it? Q into E. Q2 and E1. What is the force in an electric field? Force is 1 by 4 pi epsilon naught Q1 Q2 by R square. This is the force acting onto it. Electric field is 1 by 4 pi Q1 by R square into Q2. This is the force acting on this charged particle. Now, if it is moving from A to B, let me calculate the work done by this force. Work done by the electric force. 1 by 4 pi epsilon naught Q1 Q2 by R square into the distance. But force is depending on R. So at any moment, R is not constant. As the charge is moving from A to B, R keeps on changing. And if R is changing, it means this force is changing. So we cannot calculate work done by just multiplying it with this distance. We have to integrate it. So we have to take the work done for a very small displacement, say at distance R. This is the force. Now if I move it through a very small distance dr, this will be the work done and I will call it dw. Work done in moving this dr. So total work done in taking from this to this, I need to integrate it. With proper limits. Distance of A and distance of B, we can define certain limit. Let me say this is R1 and this is R2. So it will be from R1 to R2. This will be the work done by the electrostatic force in moving it from A to B. How much this will be? 1 by 4 pi epsilon naught Q1 Q2 integration R1 to R2 R raised to the power minus 2 into dr. What will it be? Q1 Q2 by 4 pi epsilon naught. This will be R raised to the power minus 2 plus 1 upon minus 2 plus 1, so it will be minus 1 by R. So this is the work done, and this can be written as 1 by 4 pi epsilon naught Q1 Q2. If I apply the limits, this minus this, there is a minus sign, so it becomes R1 minus R2. This is the work done in moving the charge from A to B by the electrostatic force. Now, as it moves from A to B, the potential energy is decreasing. And what will be the work done by an external agent? Minus of it. See, if the charge is to be moved with constant velocity, force due to electric field is in this direction. How should I apply the force so that it moves with constant with speed? I have to apply force in this so that the net force at any moment, F due to electric field and F due to external, they are equal and opposite. Only then the net force will be zero. So if the charge is moving like this, I need to apply force in this direction to keep it moving with constant velocity so that the net work done will be zero. Net work done zero means whatever is the work done by the electric field, I will have to do equal work but minus, negative of it. Okay, so this is the work done by electric field. If I ask you what is the work done by external agent, so it will be 1 by 4 pi epsilon naught Q1 Q2 1 by R2 minus 1 by R1, because it will be minus of it. W external is minus WE. So work done by the external force is just opposite of it. And this is also the potential energy. The charge is moving from here to here. So U2 minus U1 is equal to the work done by external force. So U2 minus U1 is 1 upon 4 pi epsilon naught Q1 Q2 1 upon R2 minus 1 upon R1. Okay, so the charge moving from this point to this point, this is the difference in the potential energy. U2 potential energy when it is at B, U1 potential energy when this charge is at A. This charge remains fixed here. So this is the potential. Now from this expression, see, whenever we calculate potential energy, now two very important points are there. First one, work done is path independent. We are getting here 1 by 4 pi epsilon naught Q1 Q2 1 by R1 minus 1 by R2. So it depends only on the position vector, initial position vector and final position vector of the points wherever from this is R1 is position vector of the point from where we start, R2 position vector wherever we end. So it means it is not depending on the path followed, which means work done is independent of path. Which type of force then? Electrostatic forces. Whenever the work done does not depend on the path, we call such type of forces as conservative forces, for which we can apply the law of conservation of mechanical energy also. Okay. So 1 upon 4 pi epsilon naught Q, since the work done is depending only on path, we can also conclude that electrostatic force is a conservative force, and we can apply the law of conservation of mechanical energy. So whatever is the work done by the external agent, that's equal to the change in potential energy, or change in potential energy is equal to minus of the work done by internal forces. Keep in mind the difference. Change in potential energy is defined as the work done by external agent or negative of the work done by the internal forces. So here electric force is the internal force, electrostatic force. So minus of it is equal to the change in potential energy or work done by external. Work done by external is negative of the work done by the field. So the step is you calculate the work done from one position to another, FDR integrated, and whatever work done negative of it, that is the change in potential energy. Okay, so this is path independent. Second, another very important point, it is the difference in potential energy. Is a quantity which is more significant than the potential energy itself. Because we are saying that when the charge is moving from this to this position, the potential energy is changing, and it is changing by an amount which is equal to work done. If I say potential here, potential energy here is 10 joule, and here it is say 5 joule, so the work done is 5. If I say it is 20 here, it is 15 here, even now it is 5. If it is 100 here, 95, again 5. So it means whatever value I add to the potential energy here or here, it doesn't matter actually. What is more important is how much is the work done. Take again the example of gravity, that's much easier to understand. I keep a body on the surface and I assume that the potential energy is 0. Now I lift it up to this height, say, and the potential energy is 100. How much work is done? 100. Now I say the potential energy on the ground is 200. What is the potential energy here? So now it is 200 plus 100, 400. So actually it is the difference in the energy that is equal to the work done. So whatever choice we may have, it depends on us. Whatever is convenient, we take this as the choice of potential energy. Potential energy is always measured. If we want potential energy at this position or potential energy at this position, we need to define a standard. Where is the 0? If it is 0 here, then it is negative here. If it is 0 here, then it may be positive here. So when the distances involved are small in gravity, we take potential energy 0 on the surface and then it becomes mgh at whatever height. When the distances involved are very large, just try to recall, we take potential energy 0 when the distance is infinite, and then we define it, potential energy is the work done in moving the charges from infinity to their present position. Same way here also. A convenient reference is take potential energy 0 when the distance between the charges is infinity. Infinity means 0 force. One charge is not in the electrostatic field of the other charge. That's the meaning. So potential energy is 0 when the distance is infinite. Now how can we define potential energy at one particular position taking this as reference? Potential energy, I am taking now U1 is 0 if R1 is infinity. So what will be U2 now? 1 by 4 pi epsilon naught Q1 Q2 by R2. Or I can drop this now and generalize the expression. Whenever two charges Q1, Q2 are separated by a distance r, the potential energy is 1 by 4 pi epsilon naught Q1, Q2 by r. If it is 0 when the distance between them is infinity, that is the reference. So potential energy of two charged particles is equal to the work done in moving these charges from infinity to their present position. This we have done for two charges. If I have 3 charges, 4 charges or many other charges, then we will say the potential energy of the system is the work done in bringing these charges to their present position from infinity. So that is how we can define potential energy. So thank you. Next class we will take up electric potential. That is related to electric potential energy actually. We need not derive there any expression for potential due to a point charge because we have already done it. So this will be taken up in next class.